All right, welcome back. Today we're going to have a lecture on part one. It's going to talk a little bit about data preprocessing, and part two we're going to move on to this thing called the multivariate regression. Previously, we talked about regression when we only have one-dimensional data, but now we're going to assume and expand to multiple dimensions of data. So I'm Professor Wu. Let's get started. Okay, so previously we started talking about the concept of supervised learning, or specifically we talked about regression, where you have some kind of data and some kind of label you would like to predict. Here you have data about the bedroom, bathroom, square footage, and you want to predict the price of the house, right? So ideally you find this function that allows you to predict. You input these information and you predict essentially the price. Okay, so before we do any of the training, it is generally a good idea for us to change the data a little bit, and we're going to go over reasons why. So there are three ways of pre-processing that is common. One is turning categorical into numbers, and then center scaling, and then converting between 2, 0, and 1. We're going to discuss them one at a time. So sometimes our data are not numbers. So over here, these are the data, and we want to predict whether a person is going to play tennis or not, right? So depending on the weather, we predict the result, yes or no. In this case, since they're not numbers, we cannot do much mathematics with it, and therefore this kind of makes things complicated. So what we normally do is we take this as categories and then we convert them to numbers. So for example, we will say yes is equal to 1, no is equal to 2. You can do it backwards where no is equal to 1, but it doesn't matter. You just create a table and designate each possible outcome as a number, right? That's all you have to do, and it will automatically then you convert all these text into numbers. And over here, you have three options: sunny, overcast, and rain. Sunny, overcast, and rain. We can just say, okay, for all the sunny is equal to 0, all the overcast is equal to 1, rain equal to 2. So converting text data into numeric data with these categories of different categories as the data is as easy as just changing the same category to the same number. Okay. Of course, doing this, you don't want to do this by hand. So most of the time we would be doing it by Python. So label encoder allows you to do that. So let's say we read this tennis data, we read the file. And then after we read the file, we create this label encoder. And the idea is what we can do is we call the encoder, and we can transform and fit a particular feature. So here's Outlook, right? So notice before and after. So I transform Outlook and I transform play tennis. So notice how Outlook and play tennis are no longer text. Instead, they are numbers, right? And then I can reprint them back out. So converting these into from text into numbers is really easy to do. Okay. Okay, that's if we're not going to really run into this kind of data for this class, but for your own reference in the future, if you do run into it, this is how you would deal with them. Okay. The second way, which we are going to deal with more, is called centering and scaling. When we have various data, notice how sometimes the size can be vastly different. So these are between 2 and 1. So these are very small numbers. But square footage could be a huge number. And when we're doing regression, often this giant number gets treated very important, right? It confuses the learning algorithm, thinking that just because the number is really big, well, it must be more important. When in reality, that's not necessarily true. So, for this reason, we like to scale these numbers to roughly the same size, okay? So that the algorithm thinks that start off thinking they're all equally important. So let's see how this is done. Well, let's say that we have data, and obviously A, B about the same size, C is much, much bigger. So what we do is we basically look at each feature, which is each column, and then we subtract the center away. So that means that is called centering. So if we subtract the center away, is essentially we find the average value, which is 2. We average all these, and then we subtract all the values here by 2. We subtract by 2. That is called centering. So you move all the data near 0. So that's what's happening. Okay? Once you perform this, once you have centering, you then divide all the numbers by the standard deviation. So after you do this, the standard deviation equation is essentially the L2 norm of this. Okay. Uh, well, divided by n. Divided by n. So you look at this, you just square each value, divide by 4 because there are 4 numbers, and then you take the square root. So basically, you subtract the mean away, you subtract this, then divide by the standard deviation. So you can see here that the standard deviation, if you were to follow the equation, is square root of 1.2. So I take every value and divide by the standard deviation. This gives us the final result. So now we transform this into this, which as you'll see, all of them are going to be roughly the same size. Okay. So, yes. At this point, why don't you take out a piece of paper and see if you can do column B and get the final result here. Okay. Pause the video because the solution, the solution's in the next page, so you can check yourself. Now, again, I don't really expect you to do this pre-processing step by hand. I just want you to have an idea of how it's done. So most of the time when you do pre-processing, you could just use Python's sklearn library. You got to make sure you import this first. Once you import this, you can run, here's your data, right? Here's your data matrix. You simply call pre-processing and scale. So you just pre-process it, it will scale it, the result will automatically center and scale it for you. And you can see that center because the mean, the average is around 0, and the standard deviation are all the same, which is 1. Okay. All right. So besides center and scaling, another way to pre-process the data is if you take the data and scale every single number to between 0 and 1. And this is really easy to do. How do you scale this to between 0 and 1? You first subtract the smallest number, right? You subtract the smallest number, and then you look at the biggest number in it. You divide everything by the biggest number, and you essentially have every single number scaled between 0 and 1. Like this logic should not be very complicated. Okay. Now, of course, I also don't expect you to do that by hand. So with Python, you can call this min-max scalar. So let's say here's your data matrix X. So you just call the scalar min-max scalar, and then you transform your data. After you transform the data, notice how every single number is now between 0 and 1. Okay? So those are the 3 ways which we sometimes need to pre-process the data before we run them. Okay? All right, so now we're ready to move on to part 2, which is multivariate regression. Previously, we learned that regression is about learning this function, and we only use input of 1 dimension. Let's say that we now continue to move on to input of multiple dimensions, right? So let's quickly review the idea again. The idea is that you're trying to find a function, right, that when you put your data in, it creates a prediction. So this is your prediction, and this is the true result. So what we want is your prediction, the difference between your prediction and the true result This right here is an error. This is the prediction error, basically. And when you add up all the error and divide it by n, which is number of sample, then this is the average error. So the idea is you want to find a function that minimizes your average error, right? And in the last class, we say that this is really hard to find the perfect function. So what we do is we make an assumption that the function is in some kind of form where it's a combination of other functions. So these are other functions, and somehow we're saying this function is the combination of them, which allows us to then write our function this way. So this was a review from last class. So once we have it in this form, we end up solving a minimization problem that looks like this, where you're trying to find the vector W that minimizes your error. And then we can use this algorithm called gradient descent, where our location now, by looking at our location now and the gradient information, it allows us to predict the next location, t plus 1, next time step. Okay? And then, of course, here's the derivative. So we just take the derivative, plug it in here, and we can solve it. So that was what we learned last time. What we're going to learn today is yet a different way to solve the same problem. This is called a closed form solution. So the previous one was called the gradient descent method. Right? We learned the gradient descent. But there's a second way called the closed form. And the way we look at closed form is actually quite easy. So there's a better derivation, but I think if you can look at it the way I'm about to present, it's good enough. So here it is. The idea goes like this: you have your function. This is the function, and ideally, you want your function to basically predict x, right? So you want this to predict the true label. If you plug the first sample, you will get the first label. If you plug the second sample in, you'll get the second label, right? So ideally, you want this to equal to this. Now, I told you that this right here can be rewritten this way. So a function can be written as a combination of other functions. And like I said, this function should ideally predict the output. Now, we can pull the W out. So W is here. And this right here is, we can call this a matrix phi. And we're going to call this y. And therefore, the ideal case we want to achieve is this representation where we have the phi matrix times w is equal to y. Okay, you can actually in this case solve for w, and the way it works is if you have phi w equals to y, what we can do is we can multiply phi transpose on both sides. This actually allows us to create an invertible matrix. Don't worry about what that means for now if you don't understand. But the point is, if we have this, that means we can put an opposite of this, 1 over this, on both sides. We've put it here and we put it here. If we put it invertible, therefore, because this is the inverse of this, that means they cancel out, right? So this cancels out, which leaves you W. And then you end up with this equation of W. So we don't have to actually go through gradient descent in this case. All we have to do is identify this phi matrix. So we know phi. And then we simply times phi transpose times phi, find the inverse of that, and then multiply them out. Okay, so then you get the weight automatically. So this is an alternative approach to solve the same problem. Let's give you a quick example of how this could be done. So let's say here's the data x, here's the label y you're trying to predict. So what we're saying is, well, let's use linear regression. If we use linear regression, then 5(1)x and 5(2), 5(1) is just equal to x and 5(2) is equal to 1. So that's the definition of linear regression. And when you do that, the result function looks like this, right? If you plug x in, you have to have x multiplied by w1 and w2. Okay, So now this is our function. This is our function. If we were to plug x1 in, ideally we would be predicting y1. If we put x2 in, ideally we'd be predicting y2, right? Therefore, let's substitute x in. So this is the function where we put x1 in. This is the function where we put x in, x2 in. This is the function where we put x3 in. So ideally, x1, if you put a function in, we predict y1. If we put x2 in, ideally we put x2, right? So now we can pull w1, w2 out. w1, w2. So this right here is therefore your feature map matrix, where each one is the feature map. So if you calculate this, this matrix is equal to phi. So what is this matrix? Well, let's see. The samples are 1, 2, 2. 1, 2, 2. So we simply put 1, 2, 2 here, right? 1, 2, 2. So now we have the problem, and y was 0, 1, 2, right? So we put 0, 1, 2 here. So now we have the problem where phi times w is equal to y, just like what we saw previously, right here. We have the problem phi times w equals to y. And we saw previously that we can solve for w by using this equation. So therefore, once we know this matrix, we simply plug phi into this equation and out comes the solution w. Okay. So let's I want you to take a second and study this. Like let's take a second and then let's take a second to see if you can study this one. Right? This is basically in the case of linear, this is the case of polynomial. So take about 5 seconds, pause the video and see if you could follow along the logic of how we get this. Okay? And then once we get this, in the next slide we'll go over what do we do after we have phi and how do we get this. Okay, so take a second, try to understand what we've done so far. Okay, so here's another example. Like, so this is the linear example we were looking at. So in the end, we basically have phi times w equals to y, right? And we know that as long as we have phi, we can plug it into the equation. If you plug it into this equation, your problem is solved. So let's plug it in. Now, the first thing you need to know is when you have a matrix, you want to find the inverse. There's a trick that for a 2 by 2 matrix, the inverse of a 2 by 2 matrix is you calculate this value, the inverse of this. So 1 s times v minus t minus times u. Okay, one more time. S times v minus t times u. Okay? So this is the inverse of the determinant. And then you flip these two, s and v, making these negative, and you are able to calculate the inverse. So if you want to take a matrix, calculate the inverse, this is the formula you need to memorize. Okay? If you took linear algebra previously, this formula should have been taught. This is a very important formula. Okay. So let's look at this, right? And we want to calculate this thing. So we'll start with just this part. Phi transpose times phi. Phi transpose times phi. So at this point, you should be able to do matrix multiplication, right? And now, given that you have this, we can find the inverse using this formula, right? So we flip these two and put a negative on the diagonal, okay? And then this right here is 1 divided by this inverse alpha symbol. So resulting to give us this. So now we've calculated this whole thing. We can now plug it into the equation. So we know this part, which is this part. And then we multiply by phi transpose and y. Okay. So when we multiply this whole thing together, we get 1.5, and negative 1.5, which give us the solution W1 and W2. All right, that's equal to W. And that's it. That's the second way of solving like linear regression. From this, we conclude that the ultimate equation we're looking for is we plug W1 in and W2 in. And if we draw the line out, notice how we have 3 points, and this essentially gives you the least amount of error. Okay? So that's how this goes. All right. So now I want you to pause the video and see if you can write the code that basically accomplishes this. And instead of a linear, now we'd like you to try to use a polynomial. Okay. So you should end up something like this. All right. The key first step is for you to find phi. Okay. Pause the video. We're going to continue. All right. So what is phi? Well, phi. So phi 1 should be equals to x squared. Phi 2 is equal to x. Phi 3 is equal to 1. Right? So that's basically what I told you here. Therefore, if we the capital Phi matrix is when we plug 1 into that. So it'd be 1, 1, 1. And then we plug 2 into it. It'll be 4, 2, 1. And then it'll be 1.5 square, 1.5, 1, and then 1, 1, 1. Okay. So you can see right here is the phi matrix. Right, they're the same. Okay, once we have the phi matrix, all we have to do is take phi transpose phi inverse. So notice that inverse of phi trans phi, and then multiply by phi transpose y, phi transpose y. And that's your weight. That's it. And the problem is solved. It is actually really, really easy. Once you solved it, basically I draw this red line to see the closest fit, and that's it. That's the second approach is actually quite easy. Okay, so now that you've learned both the two ways to solve it, the closed form solution as well as the gradient descent solution, we're ready to move on to multivariate regression. So it's actually not that complicated. As long as you understand, it's just you are picking different phi matrices. Okay, so previously you only have x, but now let's say you have 2 dimensions or 3 or 4. It doesn't matter. All you do is phi 1. Remember previously phi x, phi 1 of x is just equal to x. Well, phi 1 of x is for the first dimension. For the first dimension, it's just going to be the first dimension. And then phi 2 of x, second dimension, is just going to be the second dimension. And then depending on how many dimension you have, right, 3, phi 3, it's just going to be the third dimension. But the very last one, like let's say 4, phi, you're going to plug the x in, and it's going to return 1. Okay? So when you have 2 dimension, then you basically, the first phi would just output the first dimension. The second will be the second. And then the final one will always just output 1. That's it. That is rule. Let's look at this example. Let's say we have 2 samples, x1 and x2, 2 samples in the data set. So what would it be? Well, 3 and 2. It's just going to be 3, 2. It's just exactly the same. And then the very last one, you add a 1. And the second dimension will be 1, 4. And then you add a 1. So basically, for linear, is whatever your original data matrix is, plus a column of 1. Okay, so finding the phi matrix is really easy for linear. Okay. Now, if it was larger, it doesn't matter. If it's larger right here, this is just a data matrix. and then you add a column of 1. Then you have a 5 matrix. After that, you can essentially use this equation to get the optimal solution. Now, I for the polynomial, it's harder, right? So, like for example, if you have 2 dimension A and B, and you're trying to find a feature map, the feature map looks like this: A squared, B squared, AB, AB1. So this is really complicated. I just need you to have a general idea, but in general, what you want to do is to use sklearn to generate this for you, because it's just by hand it's just too much. So if you want to do this one, it's polynomial second order, but you can use higher order, third, fourth, fifth. So the idea is you create a polynomial of certain order, and then it allows you to transform the data. So the data 5 matrix will automatically be generated for you. Okay. So if we are let let like instead of using code, I want you to at least have done this once. So at this point, let's say we have x of AB. In that case, and we have 3 samples, x1, x2, x3. Take out a piece of paper and see if you can find phi. Okay, you want to be able to find phi um, with the polynomial. Okay, if you're done, make sure you check to see if you got the same thing here. Okay, all right, let's continue. This is the solution. Hopefully, you got the same thing. Okay, so I think I mentioned this previously, that why this is so important, right? This equation here, the general form, is basically how we solve regression type of problem. And the only thing we're changing is the function assumption. We're going to assume various type of functions for various type of problems. And this is essentially how neural network works as well, where neural network is just yet a different type of function using different bases. Okay. All right. So how do you perform multivariate linear regression using Python? So you can perform it, you can solve it with gradient descent, but Python comes with its own library. So when you're at your work, you can quickly do it this way. Well, right here, you essentially find the phi matrix. Once you find the phi matrix, you can use the closed form solution. That's the simplest pure implementation that you implement yourself. Okay. And once you find the phi, you can find a prediction this way. Alternatively, if you're using a library, you can call linear regression, and you simply put your data and label in. And then once you call the coefficient, it automatically tells you the weights. So this is like 2 lines to perform linear regression. But of course, I would like you to know this, but in homework, I expect you to do it this way or with gradient descent. That's when you actually understand the algorithm. Calling this function does not mean you understand the algorithm. Okay. And if you are calling polynomial regression, all you have to do is transform the data into phi. Once you have the data as phi, you can use phi as if they are the linear regression and run linear regression on phi. Okay. All right. So in class work, go to your class data. You should be able to find the stock prediction data and the prices. So this is the data you have, and this is the stock prices you're trying to predict. Okay, and you want to essentially perform a linear regression and see if you can solve it using with linear regression. So you want to solve it 2 ways. First, use closed form, and second, see if you can solve using gradient descent. Okay. Uh, for advanced students um, that finish the previous problem, you want to also try load the diabetes data from sklearn, and then you want to predict the blood sugar level. Okay. Make sure you pre-process the data. And I think that's it. That's it. Yeah. Go and try to do these exercises. Hopefully, you will learn a lot from these prediction models. Okay. I'll see you in the next lecture.